Okay. So now we are supposed to have an open discussion and 10 minutes. Okay. Wow. Can gravity and quantum peacefully coexist? Anybody that wants to answer this question, please come up. I will start, yes. So it depends on what we mean by gravity. If we mean classical gravity, I would say the answer is no. If we mean quantum gravity, I would say the answer is yes to the question, can gravity and quantum peacefully coexist? The question, does gravity and quantum peacefully coexist? No, we don't have, I think, a good quantum gravity theory. Please, anybody who wants to add something? Sean.
Well, I guess I might say I didn't see any logical inconsistent in the semi-classical gravity theory in which you just have a classical metric with the Einstein tensor equal to 8 pi times the expectation value of the stress energy tensor. However, this experiment that Don Gilker and I did ruled out that simple theory. So whether there's other classical theories of gravity that aren't the semi-classical, I presumably there are, but I don't know. I'm not really familiar. Well, I haven't read the literature. Whether there's any other viable theory that leaves gravity, but I'm just saying I didn't see a conceptual problem in the as some other people did, but I think Epley and Hanna, but they basically assume collapse of the wave function. And if you don't collapse the wave, well, you almost have to not collapse the wave function in the semi-classical theory, because if you collapse the wave function, the T mu nu will when it collapses, it won't be conserved. So basically, we had to assume essentially an Everett view that the wave function didn't collapse in order that the T mu nu would be conserved and therefore could be set equal to the Einstein tensor, which is automatically conserved.
Yes, that's great. When I was saying that they do not peacefully coexist, I was referring to the suggestions of the experiments which were done this morning, in which you have a gravity-mediated creation of entanglement, and if the field is classical, the gravitational field is classical, that would not be possible. That's why.
Well, I'm saying, of course, it's ruled out by experiment, so it's counterfactual. But if you just did that experiment, you could just say the gravitational field was the expectation value. And then, of course, you'd get, I guess you'd get a fourth of the effect between the two. I mean, you could just have a single gravitational field in which both of the things went. And then, of course, it wouldn't destroy the entanglement. So, I mean, I'm just saying that's logically consistent, but I think that was ruled out by our experiment.
Right, thank you.
I just want to make a quick comment. It's actually even relevant to this semi-classical theory. Well, of course, there is a consistent theory that at one and the same time get everything we call quantum mechanical effects and everything we call gravitational effects. We know that because the universe exists, okay? And it's self-consistent because it exists. And there's some theory that does it right. We don't know what it is yet. I just want to make a little point, which is that the way this is set up often is that there's this big clash, right, between quantum theory and gravity, and one has to give way, and which one gives way, and maybe they both give way, blah, blah, blah. But it's worthwhile bearing in mind, and this is relevant to the semi-classical theory, that Einstein himself didn't think the equations of GR were so great. He said one side, right, the metric side, the geometry side was fine marble. And the other side, the T mu nu side, the stress energy tensor side, was low-grade construction plywood, because he knew that that wasn't an accurate and complete representation of matter, energy density, whatever was supposed to go in as the source. And so it's not so much a clash. I mean, Einstein already knew there would have to be something better to replace this kind of very simple-minded T mu nu he was sticking in. If it's supposed to be sensitive to what we call matter distribution, then quantum mechanics has to come in, as it were, to play that role. Obviously, there is a consistent way to do it, as I say, because the universe does it. We don't know how to do it yet.
I would say that if you have to change the Einstein equations, that would be a change of of the gravity, at least as we know it now. So.
I mean, I think there are sort of assumptions that come up in these foundational discussions about the incompatibility of gravity and quantum mechanics, and the fact that every situation we run into, we can either do it with quantum mechanics or we have a gravitational description, but there's no situation in which we need both outside very esoteric accelerators and things. I think that's just factually incorrect. I mean, really mundane things like the Earth and the Sun are situations that you can't understand unless you're simultaneously using gravity and quantum mechanics. Neutron stars and supernovae and the black body radiation in the early universe cosmology and the modeling of the cosmic microwave background radiation. These are all situations which we're simultaneously using quantum mechanics and gravity. There's lots of conceptual questions about how we're doing it, but we're doing it. And roughly what we seem to be doing most of the time is something like, very often something like semi-classical gravity in situations where fluctuations are small. Where fluctuations aren't small, we're doing something like just treating general relativity as a quantum field theory. We've known for a long time that general relativity is not a renormalizable quantum field theory, but we've also known for a long time that renormalizability is overrated. The current paradigm in quantum field theory says renormalizability just tells you there's an energy cutoff where the theory stops working. So we've got excellent reasons to think that we don't currently know how to do physics at the scale at which general relativity fails, as quantum general relativity fails. We know, on Planckian scales we can't do, we don't know how to do physics, sure. And it's certainly true that given the background, the no background nature of general relativity, there are deep conceptual questions about what we're doing when we calculate that don't have analogues in the rest of quantum field theory. But I think it's important to realize these are deep puzzles and profound conceptual and technical difficulties with a theory that we are nonetheless using all over the place in various places.
Yeah, I guess one could say also that when we use quantum mechanics to describe the Earth-Sun system, you're not really using quantum mechanics because it's sort of outside the boundaries of what typically we consider quantum, and vice versa. When we are looking at the behavior of photons, we're not using GR. There will be some general theory, as Tim was pointing out, but it's not going to be the ones we have right now.
Okay, so do something very specific to make the point then. Think about white dwarf stars. So the explicit physics of a white dwarf is that the star is held up against gravitational collapse by degeneracy pressure.
Sure.
So you can't solve that problem without simultaneously managing gravity and quantum mechanics.
I agree with
That's
that.
non-relativistic, but neutron stars are relativistic. You can't understand what keeps the structure of neutron stars without simultaneously using general relativity.
But you're using quantum mechanics for some degrees of freedom and general relativity for other degrees of freedom. And of course you need both, but they are not applied to the same degrees of freedom. I guess that's...
So there's a difference between keeping track of of gravitational degrees of freedom and keeping track of gravitational dynamics. And I certainly agree there are fewer cases where gravitational degrees of freedom come up. And there aren't none. Graviton polarization in early universe inflation would be an example. I agree that's rare. But my point is, I mean, you can make a coherent case to say that even something like a neutron star, there's some degree of division of labor going on. I think that's defensible. But it's a much more intimate marriage than one sometimes gets the impression. One has quantum mechanics and gravity in extremely close proximity, put it that way.
Yes, but I guess we can say they do not really overlap yet.
I don't think, if they don't overlap, they are within a hair's breadth of one another.
Oh yeah, okay.
And I'm not convinced I'm even prepared to go that far.
Good. Anybody else wants to add something? Can gravity and quantum peacefully coexist?
Well, I just want to say something against semi-classical quantum gravity then, which would be a sort of attempt to reconcile them. And I mean, you can have in many cases that quantum fluctuations, so to speak, are enhanced by certain effects. We have them, for example, in measurement apparatus. They enhance to classical size quantum effects. And so then, considering that continuous and be amplified to very large scales, then it will become very strange to have just a middle view of two metrics that describe the situation in one of the worlds. We would sort of violate what we observe, if such a thing would be.
But these conversations are always had, or often had, as if these were incredibly theoretical thought experiments. But very explicitly, we're often using semi-classical gravity because fluctuations are small. That's basically how we're modeling neutron stars. Sometimes we're using gravity in places where fluctuations aren't small, like in the Page-Gaukler experiments, like in the CME. We're not using semi-classical gravity. Then we're treating the quantum fluctuation. The point is, this is extant physics that we're doing and that's making predictions. Right, but this is stuff that we're doing, and these things are making confirmed predictions. I mean, this is not. Yeah, sure.
Okay, we have to finish it. Maybe I'll just mention it's essentially a question maybe for future. For me, when I formulate this question, the question which I had is what Eric had is his first example. The question, if I have a superposition of two different mass distribution and we have two different metrics, and then we carefully make it back so they are the same again, we will see interference or not. This is a question which I had in mind, and this is what I want to know the answer. But I don't ask for now. Now we have to thank all the speakers and go. We have 1 hour for lunch and the poster session.